The key to implicit differentiation is to isolate y prime. So in our first example, we're going to go through all the procedures to get what dy dx or y prime is. The first thing I do is set up every single term with its derivative value. So I will put d dx in front of each term, in front of the second term, in front of the third term, and then finally in front of the sixth. Then we take the derivative with respect to x, and that's the key, with respect to x of every term. The first one is simple, it's 2x. The last one is simple, it's 0. The derivative of 3x with respect to x is just 3, which leaves us with this one right here. We don't have anything in terms of x, and if I go back to my original equation, I cannot isolate y so that there's only x's. No matter how much I try, I'm going to get possibly 2 or more values of y. So we're going to take this value here by pulling the 2 out, put it in front of d dx, and take the derivative of y cubed. When we take the derivative with respect of y cubed, we're going to have to use the chain rule, because d dx of y cubed is the same as d dx of the baby cubed, and that's what that word is, baby. So I treat it just like that. I will say the overall function cubed has a derivative of 3 function squared, or 3 baby squared. Then I'll take the derivative of the baby, which in this case is y, and I will say derivative of the baby with respect to x. Now remember, we can't isolate dy dx and just do it by itself unless we know what y is. And isolating y in this problem could be a real hassle. So instead, we leave dy dx in that answer right there for the chain rule and plug it back in for this. So now I go to the next step, which is bring down my 2x, bring down my negative 2, plug in our answer from here, and then plug in the rest of what I've done. Now we want to isolate this dy dx because we're trying to find the derivative of y with respect to x. So I'm going to move my 2x over. I'm going to move this 3 over. And I'm going to move this element here over as well. When I move the 2x over, I have negative 2x. I move the 3 over, it's a negative 3. I move the negative 2 times 3 times y squared over, which is going to be divided out right here. And when I divide those out, this whole term is going to turn into 1, and I end up with negative 2x minus 3 over negative 6y squared. Now a negative and a negative turns into a positive, and so I end up with 2x plus 3 over 6y squared. You can simplify that, so it's going to read x over 3y squared plus 1 over 2y squared. But I think the easiest way would be to leave it just like that. For problem number 2, when they ask you to find the slope of a line tangent to and normal to the graph at the point 3, 2, the key to that problem is to underline the key phrases. We want the slope of a tangent line, and we want a slope of the normal. So first we're going to figure out what dy dx is. And then when we found dy dx, we're going to flip it and take its opposite. So the first step is to find the derivative of every term. d dx of x squared plus 4 times d dx of y squared equals d dx of 25. The derivative of x squared is 2x. The derivative of 25 is 0. And when I figure out the derivative of y squared, that's going to be a chain rule problem. Put the 4 there for right now, and we'll put in the rest later. When I take the derivative of y squared, that's going to be 2y. Then you have to take the derivative of the baby, and the baby in this case is y. So the derivative of y is going to be written as dy dx, or you could write 2y y prime. So we're going to put 2y dy dx, dy dx. So we're going to move the 2x over, and we're going to move 4 plus 2y over. So I have 8y dy dx equals negative 2x. And now I can divide by 8y, and the derivative of y with respect to x is equal to negative 2x over 8y. But we want to calculate this when x equals, and in the problem they said x was 3 and y was equal to 2. So now I just plug those numbers in, and I'll have negative 2 times 3 over 8 times 2, or negative 6/16, or negative 3/8. Now that is going to be the slope of the line tangent. So now let's do the slope of the line normal. The slope of the line normal is going to be negative 1 over the slope of the line tangent. So we'll end up with negative 3/8 as the denominator, and then you flip and multiply, and you're going to get 8/3. And that is the answer for part 2. Solution is shown. Here's our 2x, here's our 8y, and there's dy dx, and there's the 0. Then they just isolated y prime, and when they did, they found out what y prime was equal to when you apply 3, 2 to the x and the y. And so you put the 3 there, and you put the 2 there, and that's where they get the slope of the tangent line. Then they just flipped it and took the opposite to get the slope of the normal line. For example number 3, notice right here that you've got a product of 2 factors, so you're going to have to use the product rule to find the derivative right there. But the rest of it is fairly straightforward. Again, set up with d dx every term, and then after you have done that, I'm going to pull the 2 out in front of this, d dx of x times y plus d dx of y cubed, and d dx of 5x. I'll do the easy ones first. The derivative of x cubed is just 3x squared, and the derivative of 5x is just 5. But based on the previous examples, I can probably do this one in my head. The baby is y, and the overall function is the baby cubed. So for d dx of y cubed, I will write down 3y. Then I'll take the derivative of the baby, which is y, and we write that as dy dx, better known as the derivative of y with respect to x. Now the only thing left to do is to figure out this whole value here. So to do that, I'll use the product rule. And off to the side, I do my work. So starting with x and y, I'm going to put down d dx, set up my table very quickly, write down f prime g plus fg prime, and then I'll just put down what f is, which is x, what f prime is, which is 1, what g is, which is y, and what g prime is, and this is key, it's going to be either y prime or you can write dy dx, which is what I prefer. Then you just plug in every value. F prime is 1. Use parentheses for g, which is y. Use parentheses for the rest. The f value is x, and the g prime is dy dx, or if you want, you can use y prime. Now we have what the solution will be that I'll put over here, return back to the beginning, put a negative 2, and then put in y plus xy prime, or y plus x dy dx. A notational thing to remember is that if you use dy dx in part of the problem, use it in the whole problem. Don't vary and put a y prime here and then dy dx there. That can get pretty confusing. Now the only step left to do is to isolate dy dx. So let's get rid of the 3x squared and get rid of the 2y right here. And when I do, I'm going to have on the right-hand side 5 minus 3x squared. And then I'm going to have a negative 2y, which becomes a positive 2y on this side. The only thing left now is x, and that's actually a 2x because I had negative 2 multiplied by that. So it's a negative 2x dy dx. And then I have plus 3y dy dx. At this point, I'm going to go back to my rules, and at the top it said collect all the y prime or dy dx terms on one side, which we've done. Now we're going to factor out y prime or dy dx. So the dy dx is common to all of it, and I put in the negative 2x plus 3y, and now I can factor out, or having factored out, I can now divide out the negative 2x plus 3y. And I'll divide here, and when I do, I'll get negative 2x plus 3y, and negative 2x plus 3y here becomes 1. So now I have the solution to the problem. It's right there. We're not quite done because they asked us to evaluate this at the point 1, 2. So I'm going to put a bar right here and put x equals 1, y equals 2. That's the notation we use to be able to evaluate a derivative at a specific point. And so you can finish the rest of the problem. 5 minus 3, 1 squared, plus 2 times 2. And all over negative 2, the x value is 1, and the y value is 2. And when you finish, you'll end up with your answer. And the answer on this one came out to 6/10 or 3/5. And that's how you'll do example number 3. There's the simplified form where there is no side work shown, such as we did right here. And y prime was used all the way through. You should be able to get it from here. And when you do, you should be in pretty good shape. Notice our answer right here matches the answer right there, and it works out pretty cleanly. Whoops, I forgot one thing. There was a y squared in there, and I think I dropped it somewhere. Or did I? Now that's interesting. The mistake I made was right here. The y cubed has a derivative of 3y squared, so I forgot to put that in there. So we'll have to put the squared right here. And then when we carry to the other side, this is going to be a y squared down below. And so we have a y squared there, we have a y squared there, a y squared there, and that's going to change this into a squared right there, and the answer still comes out to 6/10 over 3/5, and that's how you'll do example number 3. For example number 4, they ask us for the second derivative, and so I'm going to underline that to make sure I remember to do that. And we're going to set up again d dx of x squared and d dx of y squared. That's where we're going to need to use the chain rule right here, and d dx of 3. Question comes up, do you have to write out the d dx over and over? Yes, you really do. So the derivative of x squared is 2x, and the derivative of y cubed, we already did this in the previous problem right here on number 3, and we know that's going to be 3y squared. Don't want to forget the squared this time. And then the derivative of the baby, which is simply dy dx. And then we're going to have the derivative of 3, which is 0. Now we need to isolate dy dx. So when we do, we're going to move that 2x over and make it a negative 2x. And we're going to divide by 3y squared. Or we can write this negative 2x times, and be sure that 3 goes into the whole element here. It's 3, and then a y, and then the y is to the negative 2. I'm sorry, that should be a 1/3. There we go. Because I have an invisible 1 up here, that 1/3 is going to carry over as a 1/3 here. So we'll clean this up, and it ends up being negative 2/3 x y to the negative 2. Now I think this is a much easier thing to take the derivative of than to try to use quotient rule on this right here. So the next step is to take the derivative of the derivative, and so d dx. And in this case, I want you to notice this whole thing is equal to dy dx. So we're going to say d dx of dy dx, or of just y prime. And that is going to give us d squared y